Okay, today we're going to go through a question on graphs, and that is to determine if a graph is bipartite. Now, for those who don't know, a graph is simply just a bunch of nodes and edges that connect them, and a bipartite graph is one we can split into two. Where everyone in this set here, this U set, the blue set, none of them are neighbors to each other. They're only neighbors to other nodes in the green set. So if we were to look at this example, this would not be a bipartite graph because we have this here. So 5, if we call that blue, then this one would have to be green, right? Since they are neighbors, and neighbors have to be in different sets. Then 5 and 2, so 2 and 5 must be in different sets. But then 1 and 2, we've just said they have to be in the same set because they both can't be in the same set as 5. But then they're neighbors. So if this is blue, this is green, but they're the same color, it means it's not a bipartite graph. So how we're going to solve this is we're going to make use of this color idea and label all our nodes either true or false, or green and blue, same thing, we just need 2, so I'm just going to use a boolean. And if we ever find neighbors that are the same color, we just return false, otherwise it's going to be true. So how I'm going to do this, first I have to keep track of which color node it is. I'm going to initialize them all from to -1, and so for all blank in range when graph. That's how it's going to look like. And by the way, we're given the graph is a list of lists. How it looks like is if you look at this example here, so each list represents a node. So this 1, 3 represents the 0 node. Its neighbors with 1 and 3. 1 is neighbors with 0 and 2, and so on. And so this graph here is bipartite, since 0 and 2 can form a pair, and 1 and 3 can form a pair, and they're not neighbors, so it works. Whereas this example here fails. So what I'm going to do is I'm going to define a helper function, which I'll just call helper because I'm lazy. I'm going to pass in graph, I'm going to pass in colors, I'm going to pass in the color which should be, and then just a node, so say V. Since we're dealing with graphs, we usually pass in V. Now, first step is if our node, if its color, which is stored in colors, is not, so I'm going to do not color, if it's not color. The reason is there's actually 3 possibilities. Whoops. It could be -1, meaning we haven't tried it yet. It could be the color it's supposed to be, or it could be the color it isn't supposed to be. So if it's not color, then I'm just going to turn it false. So this means we've got a node that is, say, blue. It's meant to be green. So in that case, we just return false. Otherwise, we can set it to the color it's supposed to be. So this just takes care of the case where we have -1. Now we just want to loop through all the nodes it's connected to. So for, say, W in graph V, so if in this example, if we're given 0, it will go through 1 and 3. Now, if this node hasn't been examined yet, so if it's -1, meaning not examined, we're going to loop through again. We're going to go through recursively. So we're going to do the same function here, but on it again, and this is called a depth first search. So basically, we go through 6, we go to its first neighbor, we go through 4, its first neighbor, we go to, that's 3, its first neighbor, which is 2, its first neighbor, which is 1, its first neighbor, which is 5, all the others are already marked, so we just stop and go back up, like that, all the way back to 6. So if not self.helper, I'm adding the self because we're dealing with a class solution here. So I'm going to pass in graph in colors again. Now I'm going to pass in not color, because this is going to be either true or false. So since they're neighbors, they have to be the other color. And then I'm going to pass in W. So if it's not true, then I just return false. Otherwise, I'm just going to examine that colors, V and, whoops, so the color of V and W must be different. If they're the same, I also just return false. And if I get through all of these, all of its neighbors, I can return true. So now I just have to call it. So return self.helper graph colors color and then 0. Oh, sorry. I can just return true or false. I'll just return true. That's from the code. and see how it goes. There's probably going to be a mistake. Yeah, whoops. Hopefully there aren't too many more. And yeah, it's accepted. There was a slight problem, however. Passes through this case. I think it would pass through this case, but it doesn't pass through all cases because this solution assumes there are no. It assumes the graph isn't disconnected. So, for example, if we break off the 4 and the 6, it would mean it doesn't know about. It would just say, oh, there's only 6 if it were to start at 6. It wouldn't know about all of this. In which case, it would just stuff up. So what we have to do is we have to loop through. We have to make sure we visit every single node. How I'm going to do that is I'm just going to place it in the for loop. So for v in range lam graph, so it just visits every node in the graph. If it has not been visited, so in other words, if v is equal to -1, what's it going to do? It's going to call this. So if it returns as false, so not just means if it returns false, graph colors true, and then v. Now I'm going to return false. Whoops, return false. Otherwise, I can get to the end of this and just return true. Now I'm always putting true because if they're disconnected, they can clearly be in the same set. They can always be in this, say, blue set because if it's not neighbors with any of the nodes that have come before. So now I'll submit it and see what happens. Yeah, and it passes. And yeah, that's about it.